Hello, this is question 6 from the 2023 Step 2 paper, and we've got sequence Fn for n is 0, 1, 2, etc. is defined by f0 is 0 if 1 is 1, fn plus 2 is fn plus 1 plus fn, so it's Fibonacci sequence. N is greater than or equal to 0. Fine. Prove by induction that for all positive integers n, that thing is q to the n, where q is that. Okay, so we're doing all positive integers n, so we're starting from 1. So for n equals 1, we've got that q to the power of 1 is going to be f2, f1, f1, f0, which is f2 is 1 plus 0 is 1, and then we've got 1, 1, and 0. So that is valid for n equals 1. Now we need to do our n equals k and our n equals k plus 1. So q to the k is going to be fk plus 1, fk, fk, fk minus 1. And then n equals k plus 1. That means we've got q to the k plus 1, which is q times k, to the k, I mean, is equal to 1, 1, 1, 0. That's our q, and then fk plus 1, fk, fk, fk minus 1, and that is fk plus 1 plus fk, so that's fk plus 2, fk plus fk minus 1, so that's fk plus 1, fk plus 1, and what we got, fk is the last one, so that is fk plus 2, fk plus 1, fk plus 1, fk. Okay, so if valid for n equals k, then valid for n equals k plus 1. It is valid for, well, I could be saying true, I suppose, but it doesn't really matter, for n equals 1, therefore valid for all n greater than or equal to 1. Right, so that's done that bit. I mean, these things are just long-winded rather than anything else, aren't they? But that's done part, well, it's not even part 1. That's a bit weird. That's before we've even reached part 1. So it's part 0. So part 1 then. So by considering the matrix q to the n, show that fn plus 1 fn minus 1 minus fn squared, okay, is equal to that. So fn plus 1 fn, okay, right, so that's the determinant of that. So we've got determinant of q to the power n is equal to fn plus 1 fn minus 1 minus fn squared. So that's a start. And we need to show that that is minus 1 to the n. So I wonder if this is going to be, yeah, I mean, it could be. I mean, standard result, we got determinant of q to the n is the determinant of q all to the n. So I'm assuming that's what we're getting here. So the determinant of q is minus 1. So minus 1 to the n. So that fits in with this, which equals minus 1 to the n. Okay, that's fine. So we've done that. I wonder if I'll be able to get part 2 on here as well. By considering the matrix q m plus n. Yeah, I might do. I mean, it looks like it's the same thing, doesn't it? So let's try that. If not, I'll just go over, I'll pull a new sheet up. But q m plus to the power of m plus n. So that's just q to the m times q to the n. So that means we've then got, we're having to do all of, yeah, I don't know. Let's write this out. So anyway, q to m plus n. So that is going to be f of m plus n plus 1, and then f of m plus n, fm plus n, fm plus n minus 1. Okay, and then that has to be f fm plus 1 fm 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 minus 1 multiplied by fn plus 1 fn 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 minus 1. And what am I trying to get? I'm trying to get fm plus n. So that is either the top right or bottom left element of that matrix is fm plus 1 fn fm plus 1 fn. Are we just multiplying this out? As in, if we look to fm plus 1 fn, yeah, this is looking at just the top right element, isn't it, of this? I think so. Fm plus n would be fm plus 1 times fn fm. Yeah, is that? Yeah, okay. So for top right element, we've got the fm plus n is fm plus 1 times fn plus fm fn minus 1. Okay, right, so that's dropped out okay as well. Right, that's 2 bits done. Right, okay, there's a lot of bits in this part. So part 3, show that q squared is I plus q. Right, okay, so we've got, so part 3, q squared, so that was 1110, 1110. So that is going to be 2, and then 1, and then 1, and then 1. Okay, so which is equal to, yeah, that is what we want, isn't it? Because it's going to be that plus that. Just make sure that's right. So 2, 1, 1, 1, 2, 1, 1, 1. Okay, good. In the following parts, you may use without proof the binomial theorem for matrices. Okay, great. So let's go back to red again. So for A, show that for all positive integers n, f2n is equal to that. Right, so we've got quite a lot of new information here. So we've shown this thing, so that's clearly going to be of use, especially as it does fit into here. So that's nice. And we're looking for something to do with f2n. So that means we're going to want q to the 2n, isn't it? Because q to the 2n is f2n plus 1, f2n, which is, you know, what we're after. Another f2n and then an f2n minus 1. So q to the 2n looks good. So shall I go down that route? Q to the 2n, so that's I plus q to the n, which is this thing. Okay. So that is then the sum from k is 0 to n of n choose k, q to the k. Okay. So, well, when we're adding up these matrices, we're just adding up the thing that's in the top, well, in each cell, aren't we? We're just adding here, we're not multiplying. So that means I can turn that into, well, looking at the top right element again. Well, we could look at bottom left, but still, looking at top right element, we got the f2n. That is going to be the sum from k is 0 to n of n choose k, but then q to the k would have an fk in that particular element, because that's what you get in q to the k. So, okay, maybe put in where q to the k is fk plus 1, fk, fk minus 1. So just squeezing that in. But yeah, you can see how we're just adding up all of those fk's to get the f2n. So that should be, is that it? Yeah, that is definitely it. Okay, right, that was sneaky. That was sneaky. Right, B then. So show for all positive integers n, f3n, and oh, F3n again, right, okay. So I'm assuming then that we're going to be going Q3n. That seems likely, doesn't it? So we're going to have then, oh, this is going to get much more messy though, isn't it? Because we're going to have, okay, so we've got Q cubed then to the n. So that is going to be, and we want to get, well, we know about Q squareds. So let's say we've got Q squared to the n. So that is, I don't know how much I like this. Anyway, so I've got Q I plus Q to the n. I wonder if that's enough to just go in on. I might be able to just go in on that, and is that going to work? Is that going to get me the answer? I don't know, it might do. It might do. So, right, Q3n. So that is F3n plus 1, F3n, F3n, F3n minus 1. And then I'm saying that then is equal to Q to the n, and then this thing again. So the sum from k is 0 to n choose k of q to the k. So is this going to come out at anything like what I want? Doesn't look as though it will, does it? Because I haven't got any 2 to the k's in there at all. Ah, but it is an n plus k, because that is the sum of k is 0 to n choose k of q n to the n plus k. Right. So that's going to, I've got the second result. I haven't done the first result. Yeah, this is going to be the same. So this is, again, looking at the top right element. So I won't bother writing it out, but I'd write that in again if I was actually doing this with more space. So I'd have F3n is then going to be the sum from k is 0 to n choose k of fn plus k. Right, so I've shown the second one. I haven't shown the first one, so I'm going to need something different. Maybe I need to continue on this sequence here, and yeah, get something different to work off. So that would be, if I expanded that bracket, I've got a q, well, qi is just q, so I'd have a q. So let's do this again. So I've got a q plus q squared to the n. So that is equal to q, well, q plus I plus q. So I've got I plus 2q. I plus 2q. This is just going back to using this thing at the top again, to the n. So, right, this should get powers of 2 in then, shouldn't it? Because if I put this in, I'm now saying that this matrix that I had before, so this F3n plus 1, F3n, F3n, F3n minus 1. So all of that is now, well, I've got a 2q rather than an a in this, in my binomial. So I've got a k is 0 to n choose k, and then I've got a 2q to the k. So that would be 2 to the k, q to the k. And that gives me the answer then, doesn't it? So again, looking at the top right element, I'll have F3n is equal to the sum, k is 0 to n choose k, 2 to the k, and then it's going to be fk. Right, okay, so that was fine. Again, this is all going swimmingly at the moment. We've only got one bit left to go, so part C, that's what you need a new sheet for part C. Show that for all positive integers n, we've got that, and that's equal to 0. Right, so that is different to what we've had before. We don't have any of these F3n's, F2n's, things like that. So we've got a 0 there. So where are we getting zeros up until now? We were getting it in the bottom right element of Q, but then it goes away from there, doesn't it? As soon as you start moving further down the Fibonacci sequence, we don't get zeros in the bottom right. We've got it in I. We've definitely got, I mean, we got continuing looking at the top right element of matrices, then I is giving us a 0 in the top right. So that could be a possibility. What have we got inside all of this then? So if we're working towards, let's do the old put the answer at the bottom of the page, try and unpick it approach. So if we've got that, n plus k, n choose k, f, n plus k is equal to 0. So we've got all of this. So in this stuff on the left-hand side, we're happy with, well, if we've got the n plus k, we're talking about having a q to the n and a q to the k in here somewhere. We're happy with the n choose k, that's just coming out of our binomial. So how am I going to then pull all of this apart in order to, I mean, what bits, maybe leave a little bit of space in case I want to do an intermediate line. I've got a -1 to the n. The n's go on the outside, the k's go on the inside of the sum. So if I had that and a q to the n, and then I add a sum, k is 0 to n, I'll have the n choose k, I'll have a -1 to the k and a q to the k. So that's the same thing. And that would be equal to 0. Well, actually, it wouldn't be equal to 0. It would be equal to something, well, possibly I, but I to what power? Would it I to the n? I don't know. I mean, it could be, if we're going off the top right element of I, then that could be what we've got on the right hand side. I don't know. So anyway, so we've got that, but that's fitting in quite a lot of useful stuff. So how would I turn that? So this sum then, going back to the binomial, that's going to be, so what way round is all this going to be? That's a minus q to the k. So that's going to be I minus q to the n. So, okay, so that's -1 to the n, q to the n, and then I minus q to the n equals some in there. So that's working backwards. I minus q to the n. Oh my word, right, okay. So how do I want to go about doing this? I mean, that's q minus q squared. If I just put that here, okay, let's keep going backwards, because I can take that q inside because everything's to the power of n. So q minus q squared to the n, right? So q minus u squared, yeah, q minus q squared, okay, that's fine. Or do I take that minus in? Yeah, let's take, right, I can see we're coming back to this. If I take the minus in, I've now got q squared minus q to the n, which means that is I to the n. Yes, I to the n, I to the n, I to the n, I to the n. So does that now works? So I've said that I to the n is q squared minus q to the n. So that works straight off of this. Then I'm taking the minus out. Then I'm, yeah, factorizing that q to the n. Then I'm putting it into the binomial. Yeah, this all works fine. This all works fine. And then I just say, so looking at the top right element, so looking at the top right element of I to the n, which equals 0, we then get this. We get that. So yeah, I'm just combining all those things together and it just drops out. Right, okay, that came fine. Working backwards, it worked out fine. I'm not sure I would have just thought, oh yeah, well, let's go in and do this, and then pull out a minus sign and then pull out all these other bits. I'm not sure I would have picked it quite as easily going top to bottom, but going bottom to top, you can just sort of see we're so, we've done these so many times in this question in the previous parts, understanding what each one of these bits actually means, that you can just pull out each bit one at a time, put the n's outside the sum and k's inside the sum and work backwards. Right, okay. So yeah, that was not a bad question. It seems to be the way with the matrix questions in step papers that they seem a bit easier than some of the others. I don't know. I mean, maybe I just like matrices. I don't know, but it's yeah, that was quite a nice one compared to some of the previous ones.